About 2 years ago, I had the privilege of interviewing two brothers, Karan and Neel Kunjur, to discuss their new company, K2 Space. The plan? Build a spacecraft platform optimized for a mass-abundant post-Starship world. Since then, the company has grown from a bold idea to one of the most technically ambitious startups in aerospace. They've scaled to more than 160 employees, many of them from SpaceX, built the majority of the satellite in-house, and hot-fired a 20-kilowatt Hall thruster, one of the most powerful electric propulsion systems ever tested. They've secured contracts with both commercial partners and the US Space Force, and are preparing for their first major mission, Gravitas, which will debut their mega-class bus. Today, I'm joined by Neel Kunjur, K2's co-founder and CTO, to go deep into the engineering challenges behind building the largest commercial satellites ever attempted. I'm your host, Mo Islam, and this is Valley of Depth. Let's jump right in. Neel, welcome back to the show.
Thanks for having me. Always a joy.
Last time we recorded a podcast together, that was April 2023. So a little over 2 years ago, K2 was just emerging from stealth. You'd raised your seed round, and you were laying out a pretty bold thesis of building much larger, more powerful satellites for what you guys were calling, or are still calling, a mass abundant future. Tell us what's changed since then, what has stayed the same, and what kind of progress have you guys made?
Yeah, so we built the first powerful satellite. It's actually behind me on the floor right now, getting the last parts installed. So that's a huge step of progress. And in addition to that, we flew our first mission. So we went from one of those companies that talks about flying things in space to being a company that has flown those things in space and has proven that we can do what we say we can do. And one of the reasons I think you and I haven't had a lot of time to chat, and you haven't seen me at the conference circuit, is because it's taken about 10,000% of my attention to build this, right? Building everything from scratch, getting to this point. And now we're on the cusp of really that kind of first launch of the 20 kilowatt satellite that we'll talk a bit about today. And we're incredibly excited. I will say it's been definitely a challenge, but it was the challenge we expected. And so we've been hard at work doing that since the last time we spoke.
Well, let's take a quick step back. Tell us a little bit about the core thesis behind K2.
Yeah. So really it boils down to kind of what I like to call one of those like fundamental physics truths, right? If you look at most applications in space that generate revenue, a meaningful revenue or national security importance, they kind of come down to a combination of three things: power, aperture, and mass. So you think about an RF application like telecommunications, it comes down to power and aperture. That determines how much throughput your satellite has, the throughput of your overall constellation when scaled out. If you look at an imaging application, the resolution of your imager is driven by the size of the aperture, and that affects the mass of the spacecraft as well. And so even though that was a fundamental physics truth, in my opinion and many people's opinions, if you looked at the market and what was built to date, most of the companies in the space arena, both old space and new space, were focusing on platforms and spacecraft that sacrificed all three of those things, right? Small satellites that were low power, low aperture, low mass. And so you have this really interesting, I would say, duality where you have a physics-based truth and, in my opinion, a non-physics-based scarcity of the thing that people actually wanted, which was more power, more aperture. So we started K2 really to start that process, right? To start thinking bigger, building bigger platforms, building bigger systems that promise more of those three things that people care about today. And really scaling that out to the future. Every application we're going to be doing from here, beyond just telecommunications, is going to intimately depend on those three factors. And so all the technology we're building, the full technology stack, is designed to maximize those three things. And we're pretty unique in the industry in having done that.
So just for the sake of the audience, so mass, power, that's pretty self-explanatory. Explain what you mean by aperture.
Yeah. So aperture is essentially the size of your antenna or the size of your mirror or lens in some cases for an optic system, right? And that determines in many ways the total amount of power, RF power you transmit. It's a function of the power into the antenna and the size of the antenna. In the case of an imager, right, the size of that aperture determines the resolution, right, the number of photons you can collect, essentially. And so that's a proxy for volume, right? So the amount of area that you have on your satellite to be able to mount those large things, the amount of attitude control you have to be able to maneuver those large apertures, right? That's what is really required to be able to not just build high power satellites with high payload mass, but also host very large aperture systems.
So I want to talk about this concept of bigger is better, which for some may sound like a contrarian stance, but I do feel like when you guys first began discussing this idea, it did feel like a contrarian stance. But then when you look across the landscape, especially if you look at Starlink and Kuiper and how their satellite platforms have evolved, it definitely feels like, at least these larger constellations, people are moving towards a need for more power. So tell me a little bit about, what convinced you and Karan, like, that satellites need to grow in size and power, and why now is the moment to like pursue this.
Yeah. So, I mean, two things, right? One is like physics is the ultimate judge, right? It is the thing that, eventually over the long term will drive all of our decisions. And I think you're seeing that play out in the industry where, a company like SpaceX definitely understood that the Starlink that they put out maybe 5 years ago was going to be the lowest power version of Starlink that they would ever launch. And it was always a part of their roadmap. And you're seeing other companies in the industry that started with small satellite platforms also note that they have larger platforms on their roadmap. And I think where K2 was unique is we don't like talking about roadmaps. We like talking about what we're doing today, right? So we decided to start with something that was the highest power, the sort of most capable spacecraft on the market, and then build up from there. And so that's one key difference. That the second piece here is that we spent a lot of time talking to customers, right? When we first started out in the company, it was not a question of like what can we do, it is what should we do, right? We had the engineering ability to go build any type of spacecraft. We spent a lot of time figuring out what spacecraft we should build. And I think in talking to those customers, we heard common themes, right? That their existing platforms were power limited, that power was limiting the ability to deploy more capable architectures. And I think, as you all know, we announced last week a partnership with one of the largest telecommunications companies in the world, SES, to help architect their meospheres, their next generation MEO constellation that is intended to be a higher power, more capable system. And so a lot of those early conversations that we had that led us down this path are now being proven in some of what we're announcing with our partnerships with customers in the industry. And so that's why we converged on this approach. And that's why we've been so laser focused on doing it over all these years.
So I've been hearing a lot about MEO lately. Tell me a little bit about why MEO is interesting. Why MEO is an interesting orbit.
Yeah. I mean, a fun little anecdote from early in our company's history. So we, like many other companies, use Slack as our primary messaging source. And, when we were starting the company with just my brother and I, even though it was super early and it was just the two of us, we decided to start using Slack for whatever reason. And if you go back in our company's history and you look at the very first Slack message that was ever sent, it was a message from me to my brother saying, there's something really interesting about MEO. And this is before we'd really even converged on the product, before we decided what exactly we wanted to do. And what I was picking up on back then is still true now, which is that MEO is an extremely, extremely vast regime, right? It stretches from 2,000 kilometers up to GEO, basically. And it is a very, very interesting place to think about building constellations because the dynamics of how many constellations you need to get global coverage are just very different than LEO. So in LEO, the sort of min viable constellation is around 200 satellites, right? For global coverage of any capability. You generally want thousands for useful capability. In MEO, that number drops down to anywhere between 18 to 50, right? For a useful telecommunications constellation. The same concept applies to a lot of the government capabilities too, where we're proliferating a lot of really interesting mission sets in LEO. The government also wants to proliferate those in MEO and in GEO as well. And so MEO was this under-addressed regime that we found not many people in the market had the capabilities to go after, right? Because it's a very challenging environment to operate in. It's very hard to get there. And so a lot of our technology that we built from the very beginning was optimized around trying to make the unit economics of MEO work. And so that's exactly why companies like SES and others have really been a good match for us, right? Companies that have experience operating in those environments, that understand the value proposition and understand the technology that we're building to enable it.
Got it. Okay. Well, we're gonna unpack that because there's a lot for us to talk about with specifically around the MEO architecture. But I want to take another step back, and I want to. So you're at SpaceX. You decide to co-found this company with your brother Karan. Like, what inspired you to leave the company, and what inspired him? Because obviously, you guys have two very different backgrounds. And talk maybe about the moment where you've thought about all these kind of macro trends and sort of engineering challenges and sort of this paradigm shift that you're predicting is happening. Like, but what was the moment at the end of the day where you're like, hey, like we should do this together? And like, did you guys always have like a close relationship?
Yeah. So I'll answer maybe the first part of that question, which is where the seeds were planted for what eventually became K2, right? Because it was at SpaceX that a lot of the seeds for the ideas that we're pursuing now, came about. And so I worked on, really complex spacecraft at SpaceX, right? Not the sort of Starlinks. I worked on Crew Dragon, right? Which is a large spacecraft, very complex redundancy, fault tolerance, complex power systems. So a lot of the technical expertise that I gained through that program. But one of the last things that I was thinking about doing before I left SpaceX was I had two choices: was either stay, become really the first vehicle lead for a program called Deluxe Bus, which eventually became Starship, and this is back in 2019 when it was very, very early days, or leave and continue to grow my career elsewhere. And it was a challenging decision, but in the process, I learned a lot about what SpaceX's strategy was from how do you build products that are truly dual use, right? So Starlink is kind of the perfect example of what I think is a amazing business, right? Because you have this huge commercial market, but you also have products that you can use on the national security side. And that was really sort of the impetus for Starship in those early days. And so a lot of that thinking, both working on large spacecraft and seeing the opportunity of building a business like that, fed into what eventually became K2. And K2, we seek to actually operate a little bit differently in the orbits we want to occupy, right? We see SpaceX, Starlink, Starship as being kind of the perfect solution for the LEO architectures, right? It is hard to imagine a better technology to use for that orbital regime. But we want to service all the other ones, right? Everything above LEO, we think is a very interesting place to replicate some of that recipe of building technology that you can use on both commercial and national security missions. And so those seeds are planted there. In terms of my brother and I, we've always talked about doing a startup together ever since we were kids, right? And I think it became very convenient that we chose two different career paths to go down, because if you have two founders who only know how to design satellites, you're not going to be a very successful company. And in this case, I'm the founder who knows how to design satellites. My brother is the founder who knows how to sell those satellites and raise capital against it, right? So we have super complementary skill sets. And I think that's actually been probably the long-term driver of our success to date, and will continue to be the long-term driver of our success to come. Is we cover each other's blind spots in a really complementary way, and at the end of the day, we're still brothers. We still have stupid arguments, silly arguments over the probably trivial things, but for the really important aspects, we're really watching each other's back as we go build this company together.
Yeah, no, that's amazing. Well, so I want to. So okay, so you guys decide that you're going to start this company together. And I had the privilege of having one of the early conversations with you guys when it was just the two of you guys, and you just had a seed deck, and we were introduced by a mutual friend. And I remember asking about the idea. It made sense. Sort of building for sort of this post Starship world. How did you validate in those early days? How did you validate that? This is the direction we should be moving in. Did you talk to other people in the industry, potential customers? What kind of gave you that validation in those early days, which was 3 years ago? It doesn't even feel like that long, honestly.
Yeah. I think it was a lot of talking to people that we trusted in the industry, right? I think, I had a pretty extensive network from my time at SpaceX of people who are thinking about what the future of space looks like already, right? In their own regimes, in their own domains. Many of those people are founders of companies now and in our space. And through those conversations, very much realized where the places that were already being addressed were and where the gaps were. From there, I think it was really thanks to my brother that we actually started talking to a lot of the customers, at an uncomfortably early point in our company's founding, right? Which I think he really gave us the push to go out there and talk to customers. Like he himself, as a person who was just entering the space community, went to Symposium on his own when we were 2 or 3 weeks into existing, just to talk to people, right? And to understand where we could fit into, what problems we could solve that weren't being addressed. And, we built, I would say, a pretty extensive database of people that we talked to of understanding, what is the problem? Don't tell me the solution that you're looking for, tell me the problem that you're trying to solve. And from there, really first principles thinking and the sort of type of engineering that I was used to from SpaceX is how we came up with the solutions, we thought would be optimal to solve those problems. It was a pretty methodical approach, though, and I credit my brother for a lot of that in the early days of founding K2.
So let's talk about the product today. So what are you guys offering today? And then what does that look like in the future?
Yeah. So, right now we're building what's called the Mega Class Satellite Bus. It's a 20 kilowatt satellite capable of hosting payloads, multi-ton payloads, right? Up to 3,000 kilograms in the max configuration case. So really optimized for larger, higher swap size, weight, and power missions. And the interesting thing about what we're building is, historically that satellite, if you were to buy it from, a legacy manufacturer, who are the only ones who produce satellites that large, would cost anywhere between $100 to $200 million on the commercial side, even more on the national security side. We're building this product for $15 million or less, depending on how much you buy in terms of a constellation scale. And so the other interesting aspect of what we're building is it has a stackable architecture, right? So we can actually not just launch one 20 kilowatt satellite per launch, but launch up to 10. So that's 200 kilowatts of useful power deployed per launch. And we can talk a little bit about why that matters from a constellation perspective, but we're trying to maximize both things, both power per satellite and the power deployed per every launch. And so that first platform is launching, just coming up here in February. So the full spacecraft, not a sort of subscale version. It's full scale, full power with customer payloads. And then we're building on top of that all of the platforms to come, which we can talk about as well.
Help contextualize 20 kilowatts for me, right? So it's a powerful, that's a lot of power compared to what a lot of the satellites out there are. But maybe just help me understand 20 kilowatts versus what is on average a small satellite or a LEO satellite looks like versus historically what an exquisite satellite has looked like. Give me a little bit of sense of that.
Yeah, so I'll use maybe OneWeb as a comparison. So OneWeb was one of the early adopters of small satellite architectures. Actually, I think they still have the record for the most satellites per launch outside of SpaceX. So they can deploy 40 of their Gen 1 satellites per launch. Each of those satellites is anywhere from 500 watts to 1 kilowatt of solar array power, which basically means, if it's 500 watts per satellite, you're launching 40 of them, right? You're not launching that much power per launch, right? You're launching 20 kilowatts of power per launch. And so even though that's a useful architecture for deploying maybe an initial capability and an entry into service, what really matters for a telecommunications architecture is the throughput per satellite and the throughput at the constellation scale. And then, essentially how that translates to cost, right? The cost metric being the dollar per gigabit per second or dollar per watt. And so if you compare that to what we're building, right, each of our satellites, instead of being 500 watts, is 20 kilowatts, right? That's 40x. On top of that, you have, essentially the ability to deploy 10 satellites per launch. So that's 200 kilowatts of useful power per launch. And so it's just a completely different metric of power that we're deploying compared to some of those legacy spacecraft architectures that companies like OneWeb are deploying.
And, I had the chance of going to your factory over the summer. And when you walk in, and I don't know if you still have it, but you have this outline of what the future Giga-scale satellite looks like. And, it's about the size of a school bus. What does the power of that look like in the future?
Yeah, so it's pretty interesting. We've been reviving some of the sort of product sizing as we think about what's next after Mega, now that we've kind of built the first satellite. And so that platform is sort of ranging, depending on the configuration, anywhere from 115 kilowatts to 150 kilowatts of power, right? And so that'll be the highest power thing that's ever been put in space. That's not the International Space Station, right? By far the highest power satellite. And that's where the applications really transfer from being, making telecommunications architectures that previously weren't possible to now making applications that weren't previously possible. And so that vehicle is definitely something that we're designing for now, right? A lot of the components that we're building for the Mega class satellite are designed to be sort of drop in on the next spacecraft, that Giga class spacecraft. And really, that's where we start accelerating away from the rest of the industry. I think if you look at most spacecraft providers in the market right now, even if they're operating at maybe the 1 kilowatt range right now, they have a roadmap for higher power systems. But that roadmap tends to end at something between 8 and 10 kilowatts, right? And maybe they'll begin producing those spacecraft 2-3 years from now. We're launching our 20 kilowatt spacecraft next year, and we're going to be producing 100 kilowatt spacecrafts 2 to 3 years from now, right? So it's just furthering the gap in this domain between us and the rest of the market.
Right. Well, okay. So let's talk about sort of engineering one of these things. So let's just talk about Mega, since that's what you're building right now. So you mentioned earlier, this type of power historically has cost a couple $100 million plus. And then you quoted a number that was like 15 million. Now, I have to imagine that you're not buying off-the-shelf components to build your satellites. There's probably subsystems that have to be completely rethought to be able to get and work into that cost structure. Talk about that. Like how have you been able to do what the Lockheeds of the world haven't been able to do, that have historically built these exquisite satellites?
Yeah, so I think very early on, pretty much at the inception of the company, we knew that we wanted to pick a challenge that required a kind of incredible engineering ability to execute on, right? And so this is definitely that, where you can't just go buy components, off the shelf from providers. I can't go buy large reaction wheels. I can't go buy power systems, string them together into a satellite and launch it at a cost point that actually makes sense for customers. You have to build all of that from scratch yourself. So K2, in this factory behind me, we build pretty much all the subsystems here in-house. About 80% of the satellite is vertically integrated and has been vertically integrated since the inception of the company. So that's everything from large reaction wheels to Hall thrusters to high power batteries to solar arrays. And we're becoming more and more vertically integrated with time. It's part of the thesis that I never questioned, never doubted. And it does require a lot of capital, a lot of engineering talent. But once you do that, you basically build a machine and a tech stack that you can use, not just for our mega class satellite, but for all the other products that we have envisioned down the road to continue to build on that technology advantage that we have over the rest of the industry. And to use your example of Lockheed, right? Like Lockheed and Boeing and the primes, it's not like they had bad engineers. They had great engineers. They did some incredible things on the satellite side up until now and continue to do things on the mission side and the payload side moving forward. But when it came to their satellite bus programs, one big, I would say, mistake they made is they lost control of some of their supply chain, right? They started to rely on a network of vendors that couldn't quite meet the price points and the speed and pace that we're demonstrating now. And it becomes very hard to move away from, sort of that style and that model of business back to being vertically integrated once you've already given a lot of that sort of subsystem control away. And so that's kind of why I'm glad we started, from scratch being vertically integrated. We built our company around that whole principle, and we're continuing to build those subsystems today.
Talk about some of those innovations and subsystems that you've achieved so far. I mean, I've heard about your reaction wheel. Maybe start there.
Yeah, the reaction wheel is a great example of, I think, both the innovation and the thesis, right? So for a large satellite like ours, you have gigantic solar arrays. Those gigantic solar arrays mean that you have to have very large reaction wheels to do attitude control, basically pointing of that size of spacecraft. And so those large reaction wheels traditionally were made by maybe 2 or 3 companies, one of them being Honeywell. Our reaction wheel is a 100 Newton meter second wheel. Honeywell has, a 75 Newton meter second reaction wheel that is fairly public that they've, been producing for decades. And if you look at the cost structure of one of those wheels, right, it can cost anywhere from $250,000 to millions of dollars, depending on sort of the customization, the mission, et cetera. So one of the big innovations we've done is we've built not only a very performant reaction wheel, we've done it at a cost point that's just fundamentally different, right? Our first wheel that we built, the wheel that is going to be flying, that already actually flew on our past mission, that wheel we produced for under $50,000, right? And that is sort of a huge step in enabling this type of spacecraft to exist. And it's not without its challenges, right? I think, there's companies out there that have built smaller reaction wheels, smaller subsystems. I would say building a small reaction wheel is hard, but it's not quite nearly as hard as what we're doing, right? Like as you scale up the size of the disk, the manufacturing becomes more challenging, the balancing becomes more challenging, bearing sort of problems start to poke their heads and rear their ugly heads. That really, when you're operating at subscale, you never encounter. So it was a huge challenge to build this reaction wheel, but now we've flown it and we're going to continue to fly it at the price points that we're no longer just predicting, we've actually demonstrated, right, and are building at scale here in our factory.
Well, let's maybe talk a little bit about that. Like, what are some of those engineering problems that you've had to solve that smaller satellite builders just don't really encounter?
Yeah. So, dovetailing off the reaction wheel is one example, and then maybe I'll give a power example as well. Bearing instability, for those who have designed mechanisms, is one of the boogeymen of mechanism designs. It's essentially when you're spinning a gigantic disk at thousands of RPM and the bearing, that is the critical part of that assembly, starts to go unstable. That can lead to very rapid degradation of the bearing assembly. It can lead to eventual failure. It's one of the scariest types of failure modes to have on a reaction wheel. And that phenomena just does not happen as frequently when you're building smaller wheels, right? Lower inertia, it's easier to balance them. The amount of sort of imbalance and the force that disk imparts is much smaller on a smaller reaction wheel. And when you scale up the wheel and you start to deal with these larger systems, those problems become immediately present. So we had to do a lot of engineering, a ton of testing, thousands of hours of test data to gather the data that we needed to inform the design and mitigate a lot of those issues. Another example I'll use is on the power side, right? So if you're building a low power satellite, say like sub 5 kilowatts, right? You can do that with a low voltage power system. And most people in the industry do that, right? So it's a 28 volt bus, pretty easy, pretty standard. You don't have to deal with a lot of really challenging arcing effects or really bad spacing effects. At our powers, at 20 kilowatts, you inevitably have to build a high voltage power system. So our power system operates at 150 volts, right? And at that voltage, arcing becomes a huge concern. How do you deal with even device selection? And then device selection in a radiation environment, right? It's just a completely gnarly set of challenges that you never encounter if you're building lower power systems, right? So I think, two things helped us, right? One, we didn't try to build a low power system first and then build a higher power system later. We just said, hey, we have to go straight to the higher power system. We need to build that tech stack from the very beginning. And so we become experts in the design, manufacturing, and testing of high voltage power systems for radiation environments like the ones we're flying in. And that's very, very unique to high power satellites.
Okay, well, you mentioned radiation environment. And so I want to bring back the MEO conversation, right? Okay, so you've kind of thought of this like unlock in the MEO orbital regime. Historically, you have a few options, right? You either take a rocket, go straight to your destination, or you go to LEO and you get some kind of orbital transfer, or you propel yourself there over time. But then you have to go through radiation, and then by the time you're there, your electronics are fried. So, like, talk about sort of like so. Anyway, what I'm kind of alluding to is the propulsion issue that you guys are trying to solve here, which is like you have these like larger scale spacecraft that you now have to either directly, inject yourself into the kind of close enough orbital regime and then get yourself there, or you need a good enough propulsion system to get you there yourself. So what are you guys doing there, and how have you kind of solved for these issues?
Yeah, so our Hall thruster that we're building is really what I would call pushing the state of the art and the state of possible, right? It's a 20 kilowatt Hall thruster. And for those who don't know, there's tons of low power Hall thrusters out there. These are used on the Starlink satellites. They tend to range from anywhere from 1 kilowatt at the lower end to up to 4 to 4.5 kilowatts at the higher end. So what we're building is essentially 4 to 5 times the highest power thing that's ever been put in space. And so the advantages of doing that are really, present when you look at the full system cost, right? So a lot of people, when they're building a product, they'll focus very narrowly on their specific product cost, right? So I talked about our satellite cost being $15 million. That's one piece of actually the cost advantage that we're bringing. When you look at the full system cost, it includes not just the satellite cost, but the launch cost as well. And so, one example I love to use is SES. Right now, they're launching satellites for their mPOWER constellation. They launch anywhere from 2 to 3 Boeing satellites per launch. And those go basically as close as they can get to MEO, to their final target orbit. And then the satellites orbit raise from there. Unfortunately, because of that, you can only launch 2 to 3 satellites per launch because the launch vehicle is expending so much of its fuel to get to that higher orbit. So what our Hall thruster allows to do, and why we designed such a high power Hall thruster, is that we can actually insert into LEO, a much, much lower altitude with the launch vehicle, orbit raise from there, and actually much less time than it takes those existing legacy satellites to get to their target orbit. And as you said, that allows us to avoid the problem of getting fried by the interval Allen belt. And so if you look at actually what that does to the launch costs, we go from launching 2 satellites per launch now to 8 to 10 per launch. And so not only have we brought the satellite cost down, but we've brought the launch cost down significantly as well. And this is where those MEO architectures of large quantities of MEO satellites start to become possible, right? And the propulsion system is one of those key pieces of technology that enables that. That's why we kind of set out to build that from the very beginning is, we're going to build the highest power, highest thrust thing that's ever been put in space, right? And even though it's very, very hard, it is worth the challenge because of what it does on the constellation unit economic side.
Was this design decision at all impacted by sort of the general industry commentary that Starship isn't really optimized for anything but LEO at the moment?
Yeah, so I think that was something that we had a unique vantage point into, right? Any reusable upper stage that you have, even the shuttle as an example, has really great performance to LEO, terrible performance to the higher orbits. And Starship has an architecture that will solve that, right? Eventually, there will be the capability to refuel on orbit and access those higher energy orbits. But the question is, when will that be available and what will be the sort of unit economics of that service, right? And so a lot of companies, I think, that are excited about a post-Starship future are also planning to be able to manage in-space propulsion themselves. So you look at companies like Impulse, you look at companies like ourselves, we're trying to make sure that we build the technology to take advantage of Starship as it will exist in the very near future, right? And being very performant and getting a lot of mass to LEO. And then, addressing the higher orbits on our own and not necessarily being dependent on anybody else to take us there. So yes, definitely very much informed by Starship's capabilities, being a reusable upper stage.
Do you have a prediction when Starship will have refueling ready?
I feel like you asked me a similar variant to this question when we first started, which is what is going to be ready. I'm, less and less looking into the crystal ball of Starship right now, I would say, because all of our near-term business, the sort of work that we're doing with SES, work we're doing with customers on the national security side, that's all based off of Falcon 9 for the near term. And while we are engaging with the SpaceX team to basically understand what Starship is going to look like, what PES interfaces are going to look like, we aren't necessarily trying to plan around that timeline. So I don't want to hazard a guess. What I do know is that SpaceX is very much motivated to get in-space refueling working. They're a company that has demonstrated they can make the sort of impossible technology possible. So I have no doubt that they will get it working, and especially for some of the lunar missions and especially for Mars, I think it's a matter of time. But we're not necessarily planning any of our missions around that capability right now.
So in traditional kind of satellite design, swap limits drive effectively every kind of trade-off, right? You're kind of thinking about these things from the ground up. I'm curious, when you think about your own subsystems, how much of these are and you're kind of building them and you're building these subsystems from the ground up. How often are you thinking about, we can go heavier and simpler versus robust solutions, or we don't need to get the space grade version of that. I think we can use a terrestrial version of that, and it will work. How much quote unquote innovation is happening from the sense of it's innovation by being simpler, right? It's not taking the most innovative product in every single piece of the subsystem. Talk about that for a second.
Yeah, so I would say it permeates every single trade study that we do, all the way down to the lowest level component, right? So this is where, again, the vertical integration helps us, because we can make these trade-offs of mass versus cost, not just at the integrated spacecraft level, right, where other companies might be able to do that, but I can make that trade-off all the way inside of the reaction wheel, right? So again, going back to that example, it's also a great example of a sort of an engineering decision that's very much mass versus complexity driven, right? So reaction wheel, big inertia disk, the thing that determines how much momentum storage it has is the speed at which you spin it in the moment of inertia of the disk, right? So if you look at a Honeywell wheel or a legacy large reaction wheel, those spin at very, very fast speeds, so around 6,000, 7,000 RPM, so that they can reduce the moment of inertia and effectively the mass of the disk and the mass of the overall assembly. So at K2, when we revisited that trade, because we were designing the reaction wheel ourselves, we actually dialed that needle in the opposite direction. We said, we're going to spin this disk super slow, around 1,500 to 2,000 RPM, and we're going to make the disk heavier, right, to compensate for that and still get the same momentum capacity as one of those legacy wheels. And what we got for that was a really interesting set of optimizations, right? So one, because you're spinning slower, your overall bearing lifetime is significantly increased, right? Your bearings see just less revolutions per mission. But also, your vibration goes down by orders of magnitude just by spinning slower. And for missions that demand, very, very precise pointing performance, like all of our national security missions, payloads that have very sensitive pointing requirements, that is a huge simplification on the overall system. Now I need less complex isolators. I don't need as much sort of nuanced design and control algorithms that add time to development and complexity and cost. And the final thing, right, is in spinning slower, I actually reduce my thermal load into the system as well. Right? So it's a very simple optimization that you can make if you own the component and you're applying that all the way at the lowest level, but it results in a ton of benefits on complexity, on speed, on overall robustness and reliability of the system. And we're not just doing that in the reaction wheel, right? We're doing that everywhere. Every single electronic piece part that we select, every single structure that we design, every mechanism that we design, we're applying that same philosophy of questioning the constraints that really plagued our predecessors in doing a lot of these trade studies on more mass constrained systems.
How are you recruiting the talent necessary for these niche challenges, right? It's from the very get-go, you're talking about fundamentally changing the architecture of these satellites and redesigning them from the ground up. Who's doing it?
Yeah. So I think if you look at the people that work at K2, you'll notice a common trend, right? One is there are people at K2 that could have started entire companies around what they do on their own, right? So that's kind of one of the first qualifications I looked for when we were first hiring the early team. It's are you good enough at what you do that you could start a very successful business around just that, right? And actually be, maybe even a venture scale business in just what you do, right? The second piece that I look for in some of these interviews is, can you actually teach me about what you do at a level that makes me almost uncomfortable with your technical depth, right? So I don't claim to be an expert on many things. I think I like to say that I know a little bit about a lot of things. But in these interviews, can you push me in my technical depth on what you do? And the final piece, I think that's super important and led to a lot of the early pull of the company was, will people want to work for you, right? Are there people in the industry that I can point to that would say, yes, I would love to work with Raphael, right? Our head of propulsion who designed the Hall thruster. Or I would love to work with Drew, our head of structures and mechanisms. And do you have a reputation in the industry for being a talent magnet already before you join K2? And because of that approach, I think we were able to actually build a lot of talent momentum that then attracted other people who want to work with engineers that they think are the best in the industry, right? And so that's kind of led to our talent depth that we've had to date. And the final piece I'll say is that, if you're trying to convince somebody to leave, companies like SpaceX, companies like Astronis, companies all around the industry who are already working on pretty cool things, right? They're working on pretty cool spacecraft. You have to sell them on a vision that what you are working on and what we are working on at K2 is cooler than anything else that they could ever do. Every hour that they spend here is going to be more impactful than an hour that they could spend anywhere else. And I think we've done a really good job of telling that story, right? Because we're not trying to build the same Smallsats as everybody else. We're not even trying to just focus on satellite buses, right? We have a much bigger vision, a long-term vision that I think people get really excited about when they join the company.
How large is the team now?
Yeah, so we just recently crossed 160 people, which is mind-boggling to me. I think as a founder, you always kind of feel like the company is still as small as you remember it being in the early days. But a lot of that sort of talent that we've brought on is to scale the program, right? I think we've proven that we can build the first satellite. We've proven that we can launch hardware in space. And now we need to manufacture at a caliber that matches the engineering design that we've done to date. So we've been scaling up a lot of our manufacturing teams, scaling up teams for new products that we're developing as well. So a lot of that growth in this last year has come from that. And we're going to keep the team, relatively small. It's hard for me to imagine us being, as large as even, SpaceX was when I was at the company. But, as we get more opportunity, line of sight to more products, we'll grow very thoughtfully and carefully as well.
So let's just spend a few minutes on the mission, the first mission, and then the upcoming mission coming up. So earlier this year, you flew hardware on orbit as part of a demo. Like, what systems did you test, and what were some of the key takeaways from that mission?
Yeah, so we had a pretty, I would say, successful mission earlier this year, and the goal of that mission was really to take a lot of the core technology that we're developing in-house and get heritage on it, right? So we actually got very broad coverage of pretty much all of the avionics that we're developing, a lot of the mechanisms that we're developing with the hardware that we chose to fly in that flight. So in that mission, we flew a lot of our core avionics components, so our high performance in-house sort of radiation tolerant compute node, a lot of the lower level compute devices as well flew on that mission, in addition to a motor controller in our reaction wheel, so an actual full mechanism that we were spinning. And in addition, we don't often talk about software as much, but the demonstration was actually equally important for demonstrating our in-house software development capabilities as well in the full control stack to control, a full satellite. So that mission launched in January, operated very successfully, where we demonstrated pretty much all of our primary and secondary mission success criteria, showed that a lot of those core building blocks that are now replicated throughout the larger spacecraft behind me work as intended. And demonstrate a lot of our operational capability as well to operate these satellites, doing things like software updates live, in the field, which is a critical capability that we'll need for our constellations. So we took a ton of risk off the table with that mission, produced flight hardware, proved that we could do it, took all of those lessons learned and applied them to this next vehicle.
And the next mission is taking place Q1 of 26, you said?
Yep.
And
so it's launching.
Yeah. Go ahead.
Yeah. So that'll be, we're calling the mission Gravitas. We've talked a little bit about it publicly, but that'll be launching in February on a cake topper slot on Transporter 16 that we've procured. And that is a very unique mission for the industry. One, because it's a very large spacecraft, right? And one of the largest things, I think, to be launched in the cake topper slot on a transporter mission. But also because of what we're going to be doing after that. So after we'll insert into LEO in a sun-synchronous orbit, operate there, do some very interesting payload demonstrations for a lot of our payload customers, and then actually demonstrate that orbit raise from LEO to MEO. That's so critical for a lot of these MEO architectures moving forward with our high-power propulsion system. So as far as I know, we're the first company to do that maneuver. And we're going to be getting a ton of data along the way of what that radiation environment looks like, which is equally important to some of the payloads that are flying on our mission. And the other thing that's really interesting that I think we're going to be pretty proud to demonstrate is that we're launching 12 payloads on this mission, right? Not just one, not just two, but 12 payloads. So really showing the ability to host large quantities of payload mass, but also interface with 12 different payloads from 12 different people that have 12 different interface specifications, right? So one of the big challenges of being a satellite bus designer is that payload interface. And can you standardize it? Can you drive an interface that everybody can adopt and everybody can use? And we've demonstrated that in our ability to integrate, get all 12 of those payloads successfully talking through our avionics stack, through our software stack. And we're excited to showcase that on orbit on this mission as well.
How long do you expect the orbit race to take?
Yeah. So this particular orbit raise, we may take our time, right? So we're actually going to be pausing at certain points along the way just to gather data from some of the radiation sensors that we're going to be flying. I think, getting data on that environment is going to be one of the sort of most important moats we build as a company. Very few probes have ever flown in MEO. It leads to huge uncertainties in the environmental predictions in that area. And so getting that data is going to be pretty critical. So we're pausing for weeks at a time at different hold points from 2,000 kilometers, 4,000 kilometers to 6,000 kilometers. But if we were to go full bore, basically transfer time, it would be about 2.5 months to get from our insertion orbit to the target orbit.
Got it. All right, maybe take some photos along the way at those pauses. What is this a DoD focused mission, commercial mission, both? Is that something you can talk about?
Yeah. So just like our platform is meant to be dual use, this mission is actually a great example of that, right? So it has commercial customers that are flying commercial payloads to demonstrate technology for constellations in the future, mostly in the telecommunications arena. It also has national security customers that are interested in demonstrating and testing out new technology, as well as, just like us, gathering more data on the environments. So I can't speak to the specifics of what those payloads are, but I can say it's an array of sensors, new hardware that's being tested in MEO for the first time, and then on the commercial side, some really interesting connectivity payloads that will, be a core part of some of the future constellations we're working on with them.
Once you've proven out the systems in this mission, talk about sort of, you're sitting in a gigantic factory right now. What is the scale? Talk to me a little bit about what the scaling plan looks like, scaling sort of the manufacturing and the production line.
Yeah. So we definitely have kept a very, very close eye on what our demand forecast looks like for 2027 and 2028. I can tell you right now that we will not be able to scale up fast enough to meet the demand of what we think we can provide the industry on the national security and commercial side. So we're intent on scaling thoughtfully. Our approach is to basically take the technology that we've designed for manufacturability from the start and scale it up over the next 2 years, eventually getting to a target production rate of about 100 satellites per year in the factory that you see behind me. And so that's what's really necessary to enable the constellations that we're providing for both our commercial and national security customers. And it helps that we have a very deep manufacturing team that has that expertise in scaling those, a spacecraft line up to that scale. A lot of our team comes from Starlink. Some of them come from Starship manufacturing as well. So we're investing in a lot of those really critical things that you need to invest in now to enable that rate of production. Everything from how we think about the tooling, how the satellite comes together with limited touch time, to the digital systems that we use and augment to basically track every single step that we do in the manufacturing process. So we're a very manufacturing-focused company in that sense, and that ramp rate that we'll be doing over the next 2 to 3 years is intended to demonstrate that.
What percentage of the satellite itself do you expect to be kind of standardized versus customized?
Yeah. So with a production line, right, the goal is to keep that production line continuously moving. If you look at sort of the way legacy GEO satellites were put together, generally they were made upon order, right? So a customer would go, give an authority to proceed, and only then would the production start for that particular spacecraft. What we want to do is we want a continuously moving production line, right, where the satellites are just churning off the line, and at the very end of the production line, you decide where that satellite is going, whether it's going to a commercial customer for a commercial constellation or a national security customer. And what that requires is a heavy focus on keeping the core bus the same across missions, right? So that means building a standard set of hardware that you can then build a production line around and keeping that customization at the very, very end of that process, right? So, we approach that, I would say, in 2 ways, and it's pretty unique for the industry, especially others trying to approach the standardization problem on a smaller scale. One is everybody wants to build a standard box that all payloads can fit within. That box of requirements, of power, of mass, of attitude control. The problem is with small satellites, that box is too small. I think if you look at a company like Rocket Lab, it's a perfect example of how many different variants of Photon there are, their small satellite platform, because they have to basically build a new box for missions that maybe need a little bit more power, maybe need a little bit more propulsion because of how mass constrained they are. So our first approach to standardization is just make the box bigger. I'm going to give you more power, more propulsive capability, more thermal capability, more attitude control capability than you will ever need. And you won't care because I'm delivering that at a price point that still makes your mission make sense. You're not paying for any of that extra capability, right? And so that's where bigger really, really helps on standardization. And the second piece is on the interfaces, right? So we're thinking very, very thoughtfully about designing our in-house avionics stack to make it super easy for payloads to plug in, not just saying you have to use RS-422 or you have to use Ethernet, right? We're giving them a whole plethora of options, and we're making the software intelligent enough to deal with all of those different types of payloads that we can fly, as we've demonstrated on the integration of those 12 payloads behind me.
So you're overspec'd by design, but it's okay because you're at a cost point, at a price point that customers are not used to or haven't seen before, so they're okay paying it.
Exactly, both on the sort of satellite cost side as well as the total launch side, right? We can still multi-manifest even if you're using a significant portion of that capability. So we reduce both launch cost and satellite cost to a point where they don't care if we're giving them more power than they need.
Yeah. Yeah. If you prove the model, do you expect the rise of more like large satellite startups or programs, or do you think this is something uniquely difficult that will keep competition limited in the future?
So I think if you look at the industry, right, even the Space Development Agency's tranches of satellites have gotten bigger with every tranche. I think every company in the industry right now, every startup has a roadmap to a platform that is maybe their variant of a higher power platform, maybe around 8 to 10 kilowatts. I think the key difference between K2 and those other companies is, it's not necessarily something that's on our roadmap. Our roadmap starts at a 20 kilowatt satellite and accelerates from there. So I think that our approach is just to build the thing that we know is optimal, right? Like, technology challenge aside, what is the product that we think will make our customers' missions possible today? And then build on top of that to build spacecraft that really other people cannot accelerate fast enough to catch up, right? And so, we talk a lot about sort of the satellite bus, but the satellite bus is really kind of the first product of many that we've envisioned, right? And I think some of our investors like to say there's 8 to 10 world-changing businesses that we're building within K2. I think we've maybe unveiled 2 of them so far. And so, even if there's competition, even if people start building higher power satellites, larger spacecraft, we're happy for that because it means that the physics is being proven true while we're moving on to kind of the applications and what we're doing with all of that power next. Just
2 out of 10, you're going to keep us guessing like that?
All in due time.
Okay, well, let me ask you about the future for a second. So, what do you imagine a future where satellites look less like what they have looked like, which is these kind of delicate origami folded spacecraft, or do you see more like robust kind of industrial hardware?
Yeah. So I don't even think it's necessarily the future. Like if you look at our satellite, it is a big metal box. I think one of our colleagues in the industry originally called the mega class satellite the big dumb satellite, right? Affectionately, because it is designed to be simple, right? It is designed to look industrial. It is bolted aluminum put together in an industrial way. Our production line looks more like an automotive line than an exotic, intricate spacecraft line, right? And so I think that process has already started, right? And that's one of the things that we're doing and we're investing in today. And I think that will only continue down the road, right? I think one example of what I would love to see next, right? So we use these sort of COPVs, these very high pressure propulsion tanks right now. I had a dream actually originally of using DOT tanks, basically Department of Transportation tanks, are the cylinders that you ship gas with on the road. Incredibly heavy, but those things can survive a bomb blast, right? And they're incredibly industrial. Like imagine a future where all spacecraft propulsion tanks are just that, right? We're reusing terrestrial technology that's super, heavy, right? Super robust, but we can now do that on the spacecraft that we're designing. So I see the mega class as a first step in that direction. But yes, I do believe satellites will look much more industrial in the coming years.
We touched on this very briefly with the Giga class, but when you're at 150, I know you didn't mention this, but 200 plus kilowatts of power, what and you mentioned applications. You mentioned the word applications earlier. Like, could you give us a sense of what you mean? Like, what can be unlocked by these like large scale platforms that, quite frankly, we haven't flown before?
Yeah. So I think Car and I both see K2 as developing the next generation of in-space infrastructure, right? And if you think about infrastructure today in space is telecommunications, right? That is the biggest example, the biggest sort of share of the pie of in-space infrastructure. So naturally, a lot of our near-term ambitions are focused on telecommunications. But I think it's important to think about like, what is the next generation of infrastructure in space look like? And you're starting to hear people talk about it more and more, right? So you have things like in-space computing, where you're doing a lot of processing on board, on spacecraft, in space. You even have in-space manufacturing, right? I think that's very much in its nascent stages right now. And finally, in-space energy harvesting, right? Thinking about how we harvest energy more efficiently, how we beam it down to Earth or to other places in space where we need that energy. All of those are examples of what we believe the next generation of infrastructure is going to look like, right? Beyond just telecommunications. And now the interesting thing to ask yourself is like, what do all of those things have in common? Well, they all need a ton of power and a ton of mass in order to make it viable to do that in space, right? So while we built this to go after missions that exist today, right, primarily telecommunications, and we're going to have a very successful business doing that in the coming years, we are actually building the core set of technology that's necessary to develop infrastructure across the solar system in the coming decades, right? Whether that's in-space computing, energy harvesting, or in-space manufacturing. So those are all applications that we're excited about. I think we have to exist, our platforms have to exist before a lot of those become feasible. And so we're excited to work with others in the industry that are developing the core technology pieces. We feel like we're developing one of the most important ones. But that's what's going to be enabled when we have those 100 to 200 kilowatt satellites online.
So as you think about sort of your core thesis of this like effectively paradigm shift in engineering that's taking place, do you feel like that's well understood in the space industry? I mean, you talk to a lot of engineers outside of K2. Like, do you feel like, man, like this is coming and it's still not understood, like what is happening? And it's not just satellite bus manufacturing. There's other types of engineering that should be taking place in a different way because of of our kind of future ability to put just massive amounts of mass in space.
Yeah, I would say I think many of the people in the industry that I respect are thinking about it, right? They understand this future is coming. I think the challenge for a lot of them has been how to marry that future with a business that makes sense today, right? And that's one of the things about K2 that I've often harped on is we believe we're building a practical path to a sci-fi future. There's a lot of companies out there that are just betting on the sci-fi future or just have a practical path to a boring destination, right? But a practical path to a sci-fi future is really threading that needle and trying to figure out how do you, really double down on that belief that we're going to become more industrialized. We're going to have technology that is no longer mass constrained, but then apply that to a market that exists today and to customers who have predictable buying patterns today. And so that's why our strategy and really what the combination of my brother and myself really bring to the table is I definitely have that technology roadmap in mind, and he's able to marry that with how do we get customers from where they are today to where they're going to be 5 years from now to where they're going to need to be 10 years from now to continue building their businesses.
Yeah. I have a bit of a controversial question for you, which is that, SpaceX has effectively monopolized launch. And you can argue that yes, but there will always be other launch providers for a whole host of reasons because of Starship, because of the government's need for multiple launch providers. But I'm curious, like what you think. There's a school of thought out there that says that SpaceX will own LEO with Starlink, right? They've built the satellite bus platform. They've optimized it. They're continuing to optimize it. It's getting better and better and better. And yes, it's being used for internet right now, but like that could be a platform to host all sorts of other payloads in the future, and that they're going to be able to do it at the lowest cost, and they're going to be able to launch it at the lowest cost. And then, I mean, what do you think about that? Do you think that's true? Do you think SpaceX will ultimately own LEO? Do you have a kind of perspective or viewpoint on that?
Yeah, one of the core reasons we took the direction that we did, I think a lot of the companies that are trying to replicate LEO architectures are going to ultimately be unsuccessful, right? Not only because it's very, very hard to compete with a company like SpaceX that is accelerating away from everybody, but from a technology perspective, I don't think they're being ambitious enough, right? Most of the satellites that they're developing are worse than Starlink was 3 or 4 years ago from like a capabilities perspective. So they're starting off behind and they're not able to move with the velocity that SpaceX has demonstrated. And I think between Starship and Starlink and Starshield, right, for that specific LEO altitude, really the low LEO regime below 600 kilometers, it's hard to imagine something that is better than that. And so K2 very, very intentionally decided to focus on the other orbits, right? Where we think that there is a technology problem to solve that nobody else out there is solving, one that SpaceX is not, and their architecture is not optimized to go solve. So in many ways, that's kind of how we see the future playing out, is that, yes, I think SpaceX will service most of the applications below 600 kilometers, but we want K2 to be servicing everything above 1,000, right? And yes, we will do missions in LEO where it makes sense for us in specific applications where we feel like we have a technology edge. And that will only grow with time, especially as launch vehicles like Starship come online. But we are not, explicitly trying to replicate or compete directly with what SpaceX is trying to do in LEO, mostly because, as a former employee there, I want them to succeed at what they're doing. I think their vision for that orbital regime is ambitious and really, really good for the industry as a whole.
Just to wrap here, tell me a little bit about the name K2. Where did that come from? I know you guys have a unique logo. Talk a little bit about that and what it means to you.
Yeah, so we talked a little bit about K2 existing to build the future of in-space infrastructure. And, I think you can think about infrastructure as being the sort of deployment and use of energy, right? And I often, if anybody wants a good book read, Energy and Civilization by Vaclav Smil, amazing book. It basically says that, the thesis is you can measure humanity's progression as a civilization through its ability to use energy to do useful things, right? Starting all the way back, from our first discovery of sort of energy production, of farming, all the way to now. And the interesting thing about that concept, right, of measuring civilization through the yard marker of energy, is when you start projecting even further out, right? So Kardashev was a famous astronomer, came up with a Kardashev scale for civilization that predicts out what does our energy utilization need to look like to become different categories or different levels of civilization. So a type 1 civilization can harness all the energy of our planet, right? And depending on who you talk to, we're anywhere between a 0.5 to a 0.8 on that sort of Kardashev scale. A type 2 civilization can harness all the energy of a solar system. And in order to do that, you have to build what's called a Dyson sphere. To harness the energy of the sun, they're essentially Dyson sphere or Dyson rings around the sun. And our logo is actually a Dyson sphere, and we're called K2 because we want to be a Kardashev type 2 civilization. We believe the North Star for in-space infrastructure is actually building a Dyson sphere, right? We're not, I would say, pretending about our desire to go build that. It's something actually like every few months, I'll go revisit the spreadsheet math that I did on what it would take to actually build a Dyson sphere. And every 3 months, it actually becomes more and more possible. I become more and more convinced that that is in K2's future, to go build large-scale infrastructure like that. So our name ties back to that, it references that, and all the technology that we're building is in that direction with building a Dyson sphere as a North Star.
Amazing. So it's not just because it's the two K brothers.
Definitely not. I would say that was an unfortunate consequence or coincidence. And it's also not named after the mountain. The mountain is large, and so that helps convey scale sometimes. But yeah, Kardashev type 2. Way to go.
Amazing. Well, Neel, this was a pleasure. Thanks for joining the show. It was great to chat with you for an hour versus Karan, which I talked to quite a bit. So it's great to hear your perspective and how you're building the organization and the engineering behind it, and really the lifeblood of sort of the vision of the business. So Neel, thanks so much for being on the show, and really excited to get you guys back on in a couple of years and see what else is cooking. And but by then you're going to say, yeah, we have a 500 kilowatt satellite that we're building that's the size of a building, and I'm excited for that future that you guys are trying to usher in. So
yeah, thanks, Mo. I mean, I'm always excited to come on and peel back the curtain a little bit on what we're cooking here in the factory. And yeah, I would say in a year we'll be building something even higher power than this. So I can confidently predict that.
Amazing. Well, Neel, thanks so much for being on the show.
All right, thank you.
All right, till next time.